Hi, welcome to our final project video. This is our pure pursuit F-110 with object detection. So the goal and purpose of this project was to develop a safe lane tracking navigation system. And our solution was using a pure pursuit algorithm. And then we also wanted to test LiDAR in order to test object detection. And here's a diagram. Basically, pure pursuit is only using camera. It extracts the lane and the waypoint from the lane, and that informs our steering angle. And then LiDAR informs our object detection so that we can get the velocity. All right, and here's a brief overview of our color filtering. You can see that we're extracting the range of colors that correspond to the yellow lane. Full light and half light look roughly the same, but no light, it doesn't see the lane. And for saturation, they all mostly look the same. The reason we're taking this range of saturated colors is because we want saturated yellow for the lane. And here are our results. This is for the half light, and it runs pretty much just as well as full light, but no light, it doesn't detect the lane.
Our pure pursuit takes in perception's calculated waypoint. Perception takes in the raw image from the camera, and once grabbed from the subscription, it will send it through the color filter to isolate the lane and then transforms it to bird's eye, where it calculates the waypoint, in other words, the top of the lane. Aside from basic features, the capabilities of our pure pursuit saves the previously executed steering angle so that when the car loses a lane on a turn, it will continue the turn in hopes of refining it. We use a tuning parameter K to exaggerate steering angles to optimize turns in different scenarios. Lastly, we have a pixel to meter conversion for X and Y to allow for meter to unit calculations. As you can see, the pure pursuit successfully completes the lab with RGB-based vision. You can see on both of these videos, it's successfully completing a lab. However, the logic is not perfect as it can fail with certain parameters. Here is the pure pursuit algorithm with a K of 1.7 and a speed of 1. You can see that the filter works fine. However, the car's turn cannot stay on track with the lane, and as a result, it uses the previous execution's value to continue. As you can see, it continues to do this until it eventually veers off too much where it cannot recover. With several different parameters, we have evaluated when the car fails or succeeds depending on different tunings and speeds. With 0.6 speed, the car always succeeds with Ks of 1.1 and 1.3. However, with those same Ks, but slightly higher speeds, it does not always work, with success rates being about 50%. While everything outside of this range fails, it does rarely succeed with a speed of 1 and a K of 1.7. We believe it does succeed because of the large tuning parameter K, which allows it to have Jurassic turns which can keep up with the lane.
So I wanted to briefly go over the obstacle detection pseudocode. We have a threshold, which is basically our desired degree of vision for what we consider the front of the car. Any LiDAR measurement that is outside of this degree of vision will be cut. And then within this threshold, if anything is less than an unsafe, what we consider an unsafe distance from the car, we will brake. And if not, the car will keep going. These are the basic LiDAR parameters that you could find under the ROS topic scan. Max range of 30 meters, degree of vision is 270 degrees, 0.25 per measurement, which is a total of 1,081 measurements per scan and 0.003 scans per second. The parameters we decided upon was an unsafe distance of 0.8 meters with a degree of vision of 44 degrees, 0 degrees being directly in front of the car. So it has 22 degrees of vision to its left and to its right from the center. And angle of separation is the same, 0.25 degrees. The offset we have calculated, the way we calculate the offset is using degree of vision divided by the angle of separation. This gives us an integer offset that we could use from the center in our measurement array. And this was tested using a speed of 0.6 meters per second, and K is 1.1. Here we can see a simulation of the ROSPEC where we tested to see if we could correctly get our LiDAR measurements from the vehicle. As you see, as the foam pad approaches, there is a strong dip in the distance. As it makes the corner, the distance starts to go up again. And then it will approach another foam pad, and you'll see the drastic drop once again. And so we tested a few other parameters. At first we tested only 1 degree of vision. However, this failed all of the unsafe distances. We believe that the degree is just too small, and if any obstacle lies outside of directly in front of the vehicle, it will just not see it. So then we upgraded to 80 degrees of vision. This passed the small distances of unsafe feet, but however, it failed on the large 1.2 meters. Every time it tried to do a curve, we believe that this is because it would sense the curve right next to the car, and it would incorrectly assume that it was an object in the front and stop. So then we reduced it down to 44 degrees, and this passed all of our unsafe distance benchmarks. And this is what we landed upon at the end of our project. Thanks for watching. Hope you enjoyed.